Today's lecture is about sampling, particularly as applied to low-dimensional geometry. Uh, as usual, we have our rewind through everything. Uh, Wait, where did lecture 3 go? Did I lose lecture 3? Have I never had? Oh, okay. We'll have to figure out what happened to lecture 3. Um, we've been doing some metric embedding type stuff recently. We did sparses cut 2 lectures ago. We did tree metrics last class. That one's always fun. So today, uh, we're going to talk about the sampling technique slash algorithms called epsilon samples and epsilon nets in geometric range spaces. I'll explain that in a moment. And we'll get to learn some tools along the way. We'll get to learn what's called the additive turn-off inequality. It's a lot like the multiplicative one, but additive. The proof is going to use this, the proof of the epsilon net stuff is going to use a really cool technique called double sampling. And at the end, this is probably more geometry than probability, but we'll do some discussion about VC dimension. So I'm guessing that a term like VC dimension, even if you guys haven't done much computational geometry, you must have heard of it through machine learning. Some of you maybe. No? Yes? Maybe? Okay, well, the next class is going to be about pack learning and talking about how some of these ideas and probability in general tie into learning theory. Okay. All right, so you guys remember this when we were talking about, or maybe you remember, otherwise, here it is for the first time. But when we talked about the multiplicative turn-off inequality, we were talking about how we have lots of numbers summing to a large average. And when the average is very large, then the probability of deviating goes down exponentially fast. Okay. So the exact bounds, or whatever, the bounds could have been like, oh, the odds of being bigger by 5% is roughly e to the negative 0.05 squared times the average. Likewise, the odds of being 5% lower, e to the negative 0.05 squared times that average. So we've used this many times already. So an additive version, the setup is similar but different. So again, we're looking at the outcome of n independent experiments, okay, each of which are bounded between 0 and 1. Okay, so the general theme of many independent but little kind of bounded size pieces. Okay, and rather than looking at their expected sum, I'm kind of looking at their average. Okay, so I've added x1 through xn, but I divided by n, so that's mu now. Okay, so if these were like all coin tosses with the same probability p, then mu would be p. Okay, and then epsilon between 0 and 1. So, okay, so the kind of thing we're going to bound is, okay, what are the odds that the average looks like what the average should be? So what are the odds that the empirical average matches sort of the true average plus epsilon? Okay. So, okay, maybe at a high level, I can already say, first of all, you know, the big difference is that we're doing plus epsilon and not 1 plus epsilon times mu. Okay. So it's an additive bound. However, compared to before, everything is sort of much more normalized. So for example, mu has to be between 0 and 1, right? So epsilon is sort of only interesting if it's between 0 and 1. If it's bigger than 1, then it's not really saying much. Okay, so everything has also been normalized as well. So although it is additive, it has been normalized. Okay. So the bound, then, is that this is at most e to the negative 2 epsilon squared n. Okay. Or at least that's the bound we'll work with. There's other bounds out there. All right, so what is a couple takeaways? We see epsilon squared appearing again, like before. So that'll often lead to a 1 over epsilon squared dependence in various algorithms, like usual. And here we now have something that's exponentially decreasing in n. So before for multiplicative, we had like a mu here, which made sense because mu could be very big, and we're interested in mu being very big. Here, mu, everything's normalized, so mu is small. So it wouldn't be very valuable to have mu up there. But instead, we get some exponentially decreasing thing in n. Yeah. No, any value. The opposite one is the same essentially, which is that the odds of being an absolute epsilon less is again e to the negative 2 epsilon squared n. Okay. Another thing I should point out is that for the multiplicative version, the x size being non-negative was actually important. If you remember parts of the proof, we leveraged this fact. Okay. For this, it's actually not that important that it's between 0 and 1. Okay. For example, if I took everything and I subtracted 1/2, so all the variables are between negative 0.5 and 0.5. Okay. All that would do is it would subtract 0.5 everything from everything here, and it would subtract 0.5 from mu. And so everything just downshifts, but it doesn't really change the additive difference we're going for. So actually, kind of where you start and where you end doesn't really matter, but it does matter that the magnitude between smallest and biggest is normalized to 1. So if the variables were between like 0 and 2, you would divide by half, then apply this, and then extrapolate the meaning. Okay, so what really matters is that it's bounded. Otherwise, translation is translation invariant. I would say both, because if epsilon was bigger than 1, well, once we're in the context where everything's between 0 and 1, if epsilon was bigger than 1, that's saying, oh, what are the odds that these non-negative variables are smaller than 0? In which case, this wouldn't be a very good bound. You should just have 0 here. So, yeah, it's only interesting for epsilon between 0 and 1, but I guess it holds for all epsilon. Oh, maybe negative epsilon would be an issue. That wouldn't make. Yeah, actually, it should at least be positive, I think.
By symmetry argument, why is it not possible to say that the above found, like the variables should be same, but they were different in the multiplicative version?
So in both cases, the xi's can come from different distributions. So x1 may be different from x2, may be different from x3, as long as they're independent and each individually bounded. Which I have to think back, but I'm pretty sure we've had many cases where, we set up some indicator variables based on the context, and those indicators were different from each other, I would think. But you should still be able to assess the average, and usually you do know from the context what the average should be, even if the individual xi's may be complicated. Other questions? Okay. All right, so, I guess we've already kind of done the discussion, but these are the two side by side. I'm not sure if there's anything left to point out. All right, so that'll come back into play soon, but now we can start talking about the fun stuff. Okay, so a lot of geometric problems in computational geometry are set up in this sort of range space framework where you are defined by two kind of families. One is the set of points, and the other is like the set of ranges or kind of shapes in your space that are covering points. All right, so some basic examples. So maybe the simplest one is you just have points on the real line. Okay? And your shapes are like intervals. All right, so here's an interval which contains some points. There's another interval that contains some points, and so forth. Okay? In our discussion, we actually don't really have to require R to be a finite set, I could give you a fixed set of intervals, but maybe I just say all possible intervals on the real line or something. Although if you have n points, there's really only like n squared really distinct intervals in terms of roughly what's the first point you're covering and the last point you're covering is all you're interested for each interval. Another basic example is points of the plane and disks, so perfectly circular disks, right? So whatever, it could be something like this. It can be all the disks uh, in the plane. Okay, basic thing. Another one that's maybe particularly relevant for machine learning and classification problem is half spaces. So here I've just drawn them in the plane, but they could be in higher dimensions, of course. So here's a red line that's sort of splitting the plane in half, and let's say the shaded half is the space. Okay, so this is really supposed to be the entire top right corner is the half space. Okay, all right. So yeah, it could be the family of all half spaces in the plane or something. Although I think each half space I can take one of these half spaces and sort of rotate it until it runs into 2 points, one on each side, and there's roughly only a polynomial number of really distinct half spaces for a fixed set of points. Okay, so in this context where you have some like basic shapes and points, what kind of questions might you ask? Well, you might ask a question like, is some shape a range empty? Right? Okay, that's something they'd ask. But here's a disk. Is there any points inside? Or more specifically, how many points are in the disk? Right? What's another question? Is the disk very heavy? Does it contain at least an epsilon fraction of the points for some given input epsilon? Okay, so especially for sufficiently simple shapes and low dimensions, and if you want to do things exactly, there's lots of kind of very clever data structures, things that look like binary trees and stuff. Sometimes have to transform into underlying geometry and so forth. Okay, but we're sort of interested in trying to do things approximately. Okay, so let me frame this a little more. Okay, so we're going to define a notion of measures, okay, which I'm denoting by mu. So the measure of a range R will be sort of what fraction of points it contains. Okay, so P intersection R is the number of points in a range R divided by the total number of points. Okay, and I can kind of generalize that by taking any subset Q of points and defining a measure relative to that. So now I'm just doing, how many of the points of Q does this range contain divided by the total number of points in Q. Okay, so just what fraction of points it contains. Okay. And the high level question we're interested in is this. Suppose I subsample, say with repetition, a set of points. Okay. To what extent is it going to preserve the measure? Okay. So what I would really like to do is I have a gazillion points, and I'm roughly interested in approximating the measure of all the ranges. That will roughly lead to kind of approximating some of those earlier queries, and that'll suffice. Okay. There's other machine learning implications, but we'll discuss that next time. Okay. So the question then is how many points do I need to sample? And ideally, I would like to get that sample really small. Okay. All right, so let me define then the two things that we'll try to construct. So a more straightforward one is called an epsilon sample. Okay. So Q is an epsilon sample if the measure is off by at most epsilon for every single range. That seems like the most natural thing to do. Okay, so you tell me, you can be off by 10%, so epsilon is 0.1. And I want to sample a subset of points, so I'm off by 0.1, at most 0.1 for every range. All right, so that's one. But for some applications, maybe things that look a little bit like heavy hitters, we're mostly interested in identifying which of the ranges are very heavy and stuff like that. So in that case, there are applications where an epsilon net, which is a weaker requirement, is more appropriate. So Q is an epsilon net if for any range that's at least epsilon heavy, okay, so it contains at least an epsilon fraction of the point, I'm sampling at least 1 point from the range, which is the same as saying the measure is non-zero. Okay. So in the first one, I'm trying to estimate the measure of every range. The second one, I'm just trying to make sure I hit all of the epsilon heavy ranges. Okay. They both have their respective applications. Of course, anything that's an epsilon net or epsilon sample is an epsilon net, because if something has this at least epsilon, then to have error less than epsilon, you need to hit at least 1 point, and not vice versa. But you can get smaller samples for epsilon net, as we'll see, which is why there's a trade-off. All right, does that make sense what we're trying to accomplish? All right. Okay, so, all right, this will get us warmed up. All right, let's look at the question of how to construct an epsilon sample. Okay, and in particular, how small can Q be? So here's the first observation. So we're okay. This is saying that if I don't make any assumption on the range space R, okay, then I really can't make Q that small and preserve the measure of every set. That's the claim. Okay, so if I don't really know anything about the structure of our range space, I assume nothing, then we can't get a very interesting epsilon sample, right? To have 1 minus epsilon p, that's like you basically still have the same number of points, right? Okay, so what is an example, then? What would be an example of a range space that I wouldn't be able to capture or get an epsilon sample if I only had 1 minus epsilon fraction of the original points, or less than that? What would be a bad range space? Yeah. Okay. Then let me make this particular. So okay, let me explain the suggestion. The suggestion was so for this example, suppose my epsilon was like this. Let me make it so I can draw up. Let's say that this was the epsilon fraction of points we remove in particular. Then it wouldn't capture that hyperplane in the top right there, because we're missing all the points if I omitted the ones that are circled in yellow, right? But my question was a little bit different. There may still be a way to remove 2 points that preserves all of the. So if I pick 2 points maybe roughly closer to the middle, okay, I don't 100% know, but let me choose a different one. If I remove these 2 points, okay, then this might still be an epsilon sample, because any hyperplane that sort of is missing those 2 points still has a lot of points out there. I mean, it looks like in this picture, right? So if I had let me rotate this. So any hyperplane that sort of, right, this would sort of be a relatively bad hyperplane in the sense that it's missing both of those 2 points, and otherwise it's pretty close to the boundary, right? Okay, so this almost looks like that would roughly be as bad as possible for us as far as if I remove the yellow points and then which hyperplane am I going to get most wrong, right? What I've tried to do is draw the hyperplane so it's right up against the yellow, which is basically as far as we can go while making sure it's there. And even then, we still have a lot of points up above. And I guess it depends on what epsilon is and stuff like that. But intuitively, it's not obvious that we can't have an epsilon sample that's small for a hyperplane, right? It is true that you can't just remove any epsilon fraction of points, but there may be a way to remove a smart epsilon fraction of points to get an epsilon sample for a hyperplane. So going back to this question, so the question is that uh, any set removing epsilon fractions of points won't work for a particular kind of range space. You're not constrained to the examples we just did. In fact, the examples we just did, we will actually get fantastic epsilon samples for. That's why we chose them as examples. Um, uh, so in general, P and R, P is a set of points, R is a family of subsets. Um, yeah. You can choose whatever you want. I'm asking you guys to construct a set system. Yeah, okay, that's fine. But then give me a definition of PR where that you can do that. So a system consists of a set of points and a family of ranges. So an example might be a fixed set of points in a plane and then all possible disks in the plane, right? Which induces a bunch of subsets. So in other words, just define for me a set of points and then tell me what R should be. And it's not going to be geometric. It's going to be, you can choose any collection of subsets you want. Good. Okay. All the possible subsets. That's sort of in some cases the worst kind because you have to preserve everyone, right? Okay. So a really tough range space would have all of the subsets, which I guess I've abbreviated by 2 to the p. Okay, but this can be any subset. And as pointed out, whatever points you leave out, right? So for any subset, so no matter what points you leave out, we can make Q, or the bad set could be whatever you left out, right? So you leave out an epsilon fraction. Whatever you left out, we'll choose that as our range, which exists in our family. And of course, uh, that range originally had measure at least epsilon, but it has measure 0 in the remaining. Okay. All right. So the moral takeaway is that you can't just do this for anything. Okay? But for many natural range spaces, like things of interest to people in computational geometry or in machine learning, uh, a range space can't induce all possible subsets of P. Okay? So here's like a really simple example. I've tried to arrange the blue dots in a square. Okay? And I'm saying you're not going to be able to take this disk and only surround the opposite corners but leave out the other pair of opposite corners. Right? I'm not sure how to convince you. Uh, but see, like it doesn't fit. Yeah, I can do something like this and kind of shrink wrap it to fit, but I'm still wrapping around the other 2 points when I do. Okay, so there are some subsets of these 4 points that I can't induce using disks no matter how big or small I make the disk. If I had ovals, then I could actually do it, but I can't do it with disks. Okay, so we're going to try to leverage this kind of property and get much better epsilon samples than you can do for a general family of sets. All right, so how do we quantify this? All right, so I'm going to use this notation. So given a subset of points Q, I'll write R and Q to be sort of all the intersections that are induced by my range setting Q. Okay, so R and Q is the family of, I have a subset of points and I take a disk, I intersect it with my subset of points, and that gives me whatever the intersection is. Okay. All right, so that's that. And so we have this sort of combinatorial growth function, which is, uh, so for n, g of n, it's saying, all right, choose the worst set of endpoints that induces like the largest number of different intersections. Okay. So what is the worst number of kind of distinct overlaps you can get with a fixed set of q points, endpoints, fixed set q of endpoints. Okay. So for example, and we'll prove this, if you're doing disks in a plane, okay, and you have endpoints, you can actually only generate like n cubed distinct overlap subsets. Okay. You're not at all generating all 2 to the n. All right, we'll do that at the end. That's the geometric aspect. For now, we're just going to assume that the range space has some nice growth function and see what we can do probabilistically. All right, so let's do a first attempt. This is not our final attempt at trying to construct an epsilon sample. Okay, assuming that the range space has some small growth function. Okay. All right, so let's let Q be a random sample of k points of repetition. Now, for a fixed range R, I want to use the additive turn-off bound, which I have at the bottom there, to try to argue that the measure of, with respect to Q of that range R, oh, I got it backwards, didn't I? Okay, so that the measure with respect to Q of R is concentrated, okay, as some function of K. All right, so if I want to use the additive turn-off bound, I want to come up with some kind of x1, x2, x3, x4, and stuff like that. Okay, so any ideas there? What might be good candidates for indicator variables? Yeah. Yeah, whether the ith point lands in R, right? Okay, so, oops. All right, so I'll make xi equal to 1 if the ith point is in R, and I'll make it equal to 0 otherwise. Okay. Now, if we're looking at the probability, okay, so I want to make sure it's an epsilon sample. So this is the bad event, the odds that the measured the measure with Q compared to the real measure is off by more than epsilon. Okay. All right, so what can we do? Let's see if I already wrote it down. I did not. Okay, so we can expand this out. Nothing too exciting. Now, what the absolute value is just saying is roughly doing both of these at the same time. Okay, so just so I can write less, basically. Okay, but if I applied this to that, what would I get on the right-hand side? Yeah. Yes. And because of the absolute value, which is really doing both simultaneously, we can take union bound over both. So there will be a 2 in front here. All right. Okay, so no big deal. All we've done is apply the additive turn-off bound to see what are the odds that a single range is good as a function of k. Now we just got to figure out what to choose k. All right. Good. Now, how many ranges do I really have to worry about? Well, okay. First of all, if two ranges have the same overlap with p, then they're effectively the same, right? Maybe there's two disks, but they contain the same points. They're basically the same disk. So I really only have to worry about kind of how many induced subsets there are. Okay. So what is the nice upper bound then for how many subsets there are? Uh, 2 to the size of p is 1. But it's not great. Okay. But we now have another tool to try to bound. Like, what was it for disks? So for disk, we had a much better bound of n cubed, which came from that growth function. So in general, g of size of p might be much better. Let's focus in particular on the case where g of p is better. Okay. Now, if I want to take the union bound then over all my sets, then what would be a good choice of k? So we have good odds for one set. I want to take a union bound over that many sets. Yeah, log of this times or divided by. If I just plug log of this into that, I still have some annoying terms. Now you're choosing k, epsilon squared. Okay, as usual. So if we choose log g of p over epsilon squared, then we'll get, by the union bound, we'll sum over all the ranges. What are the odds? And we know the odds, and we'll get, a constant. I was just trying to figure out what are the odds we need to get a constant. If you want to do high probability, just increase it appropriately. Okay. All right. So fine. No big deal. Although, for disks, that's telling us that we need like log n over epsilon squared points, where n is the original number of points in the plane. Okay. All right. So, so logarithmic of the growth of the total number of points over epsilon squared will give you an epsilon sample. That was really just applying the additive turn-off bound. Otherwise, the growth is just a stronger assumption. You can also show directly that if you wanted epsilon net, then the log of growth divided by epsilon instead of epsilon squared will suffice. I left that as exercise because it's not too tough to do. Okay. All right, so now the question is, can we do better? Okay, nothing too exciting has happened so far. All right. Okay, so this is the cool part. All right. So here then is what's called, this is the theorem for epsilon samples. We'll have one for epsilon nets after that. Okay. So instead of having to use log of growth over epsilon squared, it says that as long as I choose k to be at least the log of growth of 2k over epsilon squared, which is a little bit awkward, but k doesn't have to be that big for k to be bigger than log of growth of 2k, assuming growth is polynomial. I'll give an example in a second. Then you get an epsilon sample. So most of our discussion today will be about proving this theorem. So for example, if the growth was polynomial, like for a disk it was n cubed, but in general it can be n to the d. And many of these interesting systems are polynomial for some d. Then if you choose k to be roughly d log d over epsilon squared, then you'll get an epsilon sample with constant probability. Okay. But why is that exciting? That's exciting because it has nothing to do with the number of points originally. Okay. For disks, right, you could have a gazillion points. Okay. But disks have growths n cubed. D is 3. So it's really saying you only need 1 over epsilon squared points. For any particular error, you only need a constant number of points to preserve everything up to an epsilon fraction or epsilon error. That's like insane, right? It has nothing to do with how many points are the input set. Okay? So that's what's really so exciting. Okay? All right. Of course, this is again a strong condition to have polynomial growth. It comes up naturally in low dimensions, but it could be more problematic in high dimensions and stuff like that. Okay. I mean, at some level, we know we can't do all subsets, so there has to be some restriction. Okay. But it's saying that if you have some structure, you can get a very, very small sample to do what you want. Okay. For epsilon nets, you get morally something similar. So epsilon nets, just to remind you, says that I want to make sure I take at least 1 point from every disk or every range with at least an epsilon fraction of points. And there you need, again, log growth of 2k over epsilon instead of epsilon squared. Okay. And you get an epsilon net. And roughly the same thing happens for polynomial growth. Okay. The main difference is you go from epsilon squared to epsilon. All right. Okay, so those are, okay. Yeah, so those are the two the main theorems that I wanted to introduce, and we're just going to prove the first one, okay? Because the second one, the epsilon net proof, is kind of similar in structure, and it's going to end up being a homework problem, but not for like a long time because of how the schedule works out. So a month from now, you have to remember what we did. Okay, well, actually, you'll want to remember for the midterm anyway. Okay. All right. So, but any questions about the results at a high level before we start trying to figure out how to prove this thing and remove this dependence on the number of input points? Okay. All right. Okay. How do we prove this? Good question. Hopefully we have some hints. All right. Okay. So let's let Q1 be a sample of k points of repetition. Right. And A is that bad event. I'm letting, instead of writing measure of Q1, I'm writing just measure 1 to note the measure with respect to Q1. So A is that bad event we're trying to avoid. The event that we're off by at least epsilon for some range. And I'm just trying to get constant probability of error. I think in the notes, I worked out like a generic probability of error. But let's just, for simplicity, try to get a constant. And I want to show then that this bad event occurs with probability at most 1/2. Nothing simple or nothing exciting. This is probably how you would set it up as well. Okay. All right. Sometimes in this situation, I would have you guys guess what to do next. I think it's impossible. But I guess For old time's sake, does anyone want to guess? We sort of did the straightforward thing before. What we did before was the additive turn off and then take a union bound over all the ranges. That was a natural thing to do. Okay, so this proof is really cool because what we're going to do is we're going to sample another k points. Okay, so let Q2 be another sample of k points of repetition. Okay, somehow we're going to sample twice, and this is going to magically make a big difference. Okay, I'm going to let mu sub 2 denote the measure with respect to Q2. Okay. All right, now look at this event. Let's look at the event that Q1 and Q2 disagree on a range by more than epsilon over 2. Okay. So originally it was just is mu1 off from the true measure by epsilon. Now it's saying I'm taking two random samples. What are the odds that they disagree on a range by more than epsilon over 2? Okay. All right. We need another event, C. C is the event that sort of both of these things happen for the same range. Okay. So it's not actually A and B because otherwise you could have different ranges for the conditions. So it's the event that for a single range R, A mu1 is wrong and they disagree. Mu1 and mu2 disagree. Okay. All right, sort of a weird, curious setup. All right, so we want a bound probability of A, and then here's sort of an interesting claim. The claim is that probability of A is bounded above by 2 times the probability of B. Okay. Is this guessable? I don't think so. Okay. But the claim then is that our bad event is bounded above by 2 times the probability of B, which is the event that mu1 and mu2 disagree on some R. Okay. All right. Does the claim make sense? Does the claim not make sense? All right, so how do we do this? Okay, so we'll start with probability of B. Okay. Now, probability of C, or event C is just like more detailed than event B. So the odds of B occurring is at least the odds of C occurring. Okay. And A is a subset of C. So events A and C occurring is the same as just C occurring. So as soon as C occurs, A automatically occurs. So nothing going on there. But we can write this as probability of C given A times the probability of A. Okay. I just want to show that this thing is, I guess, at least 1/2, and then we'll be in good shape. Okay. All right. So if event A occurs, then there's some range R that we mismeasured by at least epsilon, right? So A implies some r such that mu1r minus mu r is greater than epsilon. Yeah. Absolutely. So okay, yeah, let's make this clear. Um, that's right. So when I say C given A, C could be for any R. So A has already happened. There's some R associated with A. And now it's like, what are the odds that C happens, which could happen for any R? And maybe to make things more confusing, A could have happened for several R's, but that just means A happens if there's several R's. And again, we just want to find some R for which C happens, knowing that there's at least one R that satisfies A. Yeah. That said, to do the proof, it is helpful to use the R in particular that has failed A, or that has forced A to happen, I mean. Okay. So there's at least one range R where the measure is off. Okay. And I want to show, we're actually going to show that for that particular R, that it's going to provoke C with probability at least 1/2. Which means I want to show that the only thing left to do is to show that mu2 and mu1 disagree on this R with probability at least 1/2. Then that would be good. So it's up to us to use the same R and we'll take advantage of that, but it didn't have to be. Okay. So this one you guys may be able to guess. All right, so you have some R, it's mismeasured. Okay. And I want to argue that mu2 and mu1 probably disagree. Okay. So mu1 screwed up R, and I want to argue that mu2 and mu1 will probably disagree.
Sort of look at the measure of points are in Q1 and the measure points are not in Q1, and then argue that like if you sample K points from these two sets joining.
Well, you started the sentence with the word can, so I can't tell you can't do anything. But
I was thinking of something sort of the form of like, oh, we will have K points where the density within these K points is say like 1/2, and then the density outside of these K points is like 1/4. So if you sample from these, your density measure will be closer to 1/4 than 1/2, something like that.
well, we have to be a little careful. So we sample Q1 and Q2 first, and then we choose R. So to kind of choose R and then retroactively change Q1 and Q2 kind of around it and stuff feels a little bit like cheating. I'm not sure if that's sound. Yeah.
Do we know that, like, from the Chernoff bound proof before that, like, Q2 probably didn't, like, screw up?
That's exactly right. So mu1 screwed up, but it shouldn't have for most. I mean, that bound is large enough by the calculations we just did that the odds of screwing up are very small. But maybe it'll screw up because there's so many ranges out there, right? But for any particular range, it shouldn't screw up. But it screwed up this particular R, but now that particular R, mu2 probably won't screw up. And if mu2 is very accurate and mu1's very inaccurate, then they're disagreeing. Okay. So, okay, so if we apply Chernoff, which is sitting somewhere in the top bottom right corner, and assuming I chose the constants, the hidden constants to be big enough, then the probability that, let's say that mu2 r minus mu r is bigger than, say, epsilon over 2, it's helpful to make it a little bit smaller, is at most, say 1/2. Okay, so it's probably 1/2 the errors at most epsilon over 2. It could have been much smaller than 1/2, but 1/2 is all we need. Okay. Now, if if mu2 does have error less than epsilon over 2, then mu1r minus mu2r, okay, is at least mu1r minus mu-r minus mu2r minus mu-r, just triangle inequality type of stuff. Okay, so you get your epsilon over 2. But the logic, I think, is clear. If you screwed up on one range, the odds of screwing up again are pretty low. So you'll get some disagreement for that range as well. All right. Okay, so that was cute. But the best parts haven't happened yet. It's so exciting. All right. Okay. So we've now kind of bounded probability of A above by the probability of B to, okay. So now all that's left is analyzing probability of B. If I could show, I guess 1/2 probably isn't good enough. Man, you get the simplest things wrong. So it's at most 1/4, and 2 times that would be 1/2, right? So, okay, but we just need to get a constant. All right. Anyone want to guess what to do? This is an impossible guess, but I find it raises morale to give you guys a chance. Okay, so this part I think is kind of surprising. At least I think this is very creative. So we're going to imagine we generated our two samples, Q1 and Q2, in a particular fashion, where in the first step, we sampled 2 K points with repetition. I'll call that Q0. Okay, so I sampled kind of the total first. Okay, and then, where did the number 2 go? There used to be, okay. In step 2, we randomly partition Q0 into Q1 and Q2. Okay, if you think about it, Q1 and Q2 are ultimately 2 independent samples of size K. All right, so we're just looking at it differently. Okay. Did I leave myself some help here? No. Oh, okay. Oh, okay. All right, so now we can do some conditional stuff. So the probability of B, right, is equal to sum over all possible choices of Q0, the probability of B conditional on Q0 times the probability of getting Q0. Okay? Which is whatever, at most whatever is the worst possible Q0, something like that. Okay? So now all that's left is we can fix Q0, which is like the original set of 2 K points that are going to get divided up into 2 sets. And then just try to show that the probability of B happening conditional on Q0 is at most 1/4, no matter what Q0 is. Okay. All right. All right. So we're fixing Q0, and I'm letting mu0 be the measure with respect to Q0, like as usual. All right. Here's what's great. How many ranges do I have to worry about within Q0? G of 2K, the size of Q0. Okay. I only have to worry at some level about G of 2K sets. We're going to get a much smaller union bound. And let's see. Whoops. Okay. Now, uh, where is this? Okay, so if you can still see this, if it's big enough, we did some log of G2K for a reason, okay, over epsilon squared, okay. So if I wanted to, okay, so let's look at this event. So I'm only worried right now about mu0. I'm not worried about the original mu, okay. In particular, if two ranges in the original set have the same intersection with Q0, they're basically going to have the same behavior here, right? Because I've now fixed Q0 and I'm comparing to mu0 of R, and I'm just worried about when I divide the points into half, what will mu1R be and what will mu2 be? Okay. So additive turnoff is going to give us the same kind of e to the negative epsilon squared k kind of thing, where k is proportional to log of G2K over epsilon squared. Okay, so probably the K would actually be half of 2K, which anyway is K. All right, so in particular, I put 8 there because it's convenient. But the point is, though, is that we'll get something inversely proportional to the number of ranges, so to speak, relative to Q0. Okay? G of 2K is an upper bound on how many ranges there are left, sort of how many kind of distinct ranges there are in terms of Q0. Okay? All right. So if we do a union bound, we have G over 2K in the denominator, so I can take a union bound over all the ranges relative to Q0. I have plenty for that. Okay, and I have this kind of thing. Okay. All right. Okay, so we kind of know that everything is going to be very stable with respect to mu0. So we first sampled 2K points that gave us this like kind of useless measure mu0. I mean, it's not something we're really interested in. But the nice thing is that because Q0 only has 2K points, I'm really now left to only worry about G of 2K different sets, different ranges because of this bounded growth. So I've kind of shrunken the universe. I've shrunk the number of points I'm worried about, but the real effect is that dramatically shrinks the number of sets I'm worried about. It's some function of K. It's not some function of the original number of points. Okay, so I can take a union bound over it, even though I only paid log of G2K. Here was the actual thing we're interested in. Mu1 minus mu2, right? First, we're just going to worry about the ranges that we've addressed. If I want to show this thing is small, right, because I want to show that mu1 and mu2 don't disagree. So I want this to be at most, I don't know, epsilon or epsilon over 2 or something like that. All right, how do I bound this term? This one is guessable. Yeah, triangle stuff. Okay, and then both of these are nice and small, so you get at most epsilon over 2. Okay, great. Now we are interested in all the ranges in the original set, right? But I can start with some range, say R prime, in my original range space, right? I want to show that this is good, right? And then I can look at R, which is the intersection with the initial point set, right? And then I can apply this argument to it, right? Mu1 of R, which is the same as mu1 of R prime, right? Because the only difference between R prime and R is that R prime shrunk down to Q0 to get R before looking at mu1, which is even smaller subset. Okay, so we know that mu1 of R prime is equal to mu1 of R, and mu2 of R prime is equal to mu2 of R, because all we're doing is intersecting with Q0 before intersecting down to Q1 or intersecting down to Q2, right? Just subsets. Okay. So what we've shown then is that this thing holds for all R and R. Okay. So somehow we're able to take a union bound over all R in some sense. It feels like we've got a bound for all R, but because when we project down to Q0, there's a much smaller set of sets we need to worry about. Okay, so this completes the proof. Yeah. Sure. So maybe it's what the hell happened in this step, right? When we changed how we generated Q1 and Q2. So Q1 and Q2 were both just randomly drawing a point out of K until they got K points. It was repetition. And all I've done here, so that means, okay, so let's look at, so maybe here's one way to think of it. So let's look at Q1. Let's look at the first point of Q1. It should be any one of the original input points uniformly at random. There should be no bias, right? So in the first way, you just draw a point. That's obviously exactly right. In the second way, you first, suppose I first draw 2K points with repetition, and then and then for the first point of Q1, I'll choose one of the 2K and one of the 2K, and then the second point we wanted the remainder, third point we wanted the remainder, and stuff like that. So if I look at the first point of Q0 in the second process, it's going to choose one of the 2K points from Q0 uniformly at random, and each of those points were drawn uniformly at random from P. So you can see that first point is completely random. And then for the second point, we've deleted 1 point from 2K minus 1. And then we have 2K minus 1 up here now, but each of those are still uniformly random above. So you can see the second point is still uniformly at random from the original point set. At some level, there's no bias entering from a kind of counter-positive perspective. If you wanted to do it slowly, then you can kind of work out and make sure probabilities cancel, but that's the best way to do it without using precious ink from the iPad. Okay. All right, so that was the proof. Other questions? Those are good questions. Something very subtle happened. Yeah.
Am I right? It feels like intuitively we're kind of ignoring all the points that aren't part of Q1 or Q2.
Yes. I mean, and that's what we're trying to prove, right? We're trying to prove that for disks in the plane, if I only sample a constant number of points, I can get constant error. That means I'm ignoring all the points, right? So that's why it's a strong statement. It's using this kind of low polynomial growth in a very clever way. Yeah. It was not. You would have to pay log of the growth, and that wouldn't be very useful. Yeah. Yeah, so there are limitations, but there's still plenty of applications where this is useful. We'll talk about machine learning and stuff like that. But ultimately, if you assume that the classifier is ultimately some, say, hyperplane or something, a relatively geometric shape, this is sort of talking about how much training data do I need to really guarantee certain errors? And so it relates to generalization. We'll talk about that more next time, right? But that would be maybe a very kind of important implication of this kind of argument. I should say learning theory instead of machine learning, but yeah. Okay, great, we survived. So again, the epsilon net proof is similar in structure. The main thing is this double sampling style of trick. But you'll of course make some changes because you'll be using one factor epsilon less and stuff like that. So I left that as I thought a good exercise because you can kind of, it would force you to understand what we just did. I mean it. I think it's good. Okay. So next question is, how do you bound G of n? Right here, I just told you G of n is like n cubed for disks and stuff like that. All right. Okay, so that brings us to this VC dimension thing. This part is not going to be so much about randomized algorithms. It's about really geometry and analyzing a couple of geometric systems and stuff like that. But of course, it has some implications. Just like sometimes we do graph algorithms, we need a few graph observations. It's kind of like that. All right. So VC dimension. VC is named after the authors of that picture. Doesn't matter. Okay. Some definitions. Okay. So. For a set of points Q, we'll say our ranges shatters Q induces all possible subsets of Q. Okay. And the VC dimension of a range space is defined as the maximum cardinality of any set of points that can be shattered by the ranges. Okay. So I have some examples to make this more clear. Okay, so let's look at intervals. Okay. So let's say all intervals. Okay, so you can pick any interval you want. So R is of infinite size. What is the VC dimension of intervals of the line? So what is the maximum number of points that can be shattered by intervals? Sorry? It's not infinite. So can you shatter 2 points? If I have 2 points, can you induce all subsets of intervals? Loud and proud? Oh, yes, okay, you can wrap them both, you can do one at a time. Okay, what if, use my head, what if there's 3 points? My face is the middle one. Oh, okay. So if you have 3 points, you can't induce, what did I do? So how did I, is there any topological, wait, am I screwed? Right. We have at least one topologist here who could help me. So if I was able to draw a circle around the 2 outer points, you would not be able to induce this with an interval. Okay? That is one of the saddest things that ever happened to me. Okay. All right. How about disks in a plane? Okay, so for disks in a plane, the VC dimension is 4. So I'm claiming that any set of 4 points can't be shattered. And we basically have 2 basic situations. One is when the 4th point is in the convex hole of the outer 3. Okay? But a circle is convex. So anything that contains the outer 3 points has to contain the middle point. So it's impossible for me to, oh God help me, contain, I did it, to contain just those 3 points. Okay? All right. So I can't do that with a circle. The other is when all 4 points are sort of in convex arrangement of each other. One point is not a convex combination of the others. And here, it's really hard to be able to do both. It's supposed to be a circle. It's really it's really hard to be able to do both of the outside pairs, because even if I could do one, right? But then when I try to do the other one I'm screwed. Okay. In general, if you could like somehow, I'll cheat and let's say I draw an oval. How did that happen? Oh my God. If I drew an oval or something like that to actually contain them, I'm cheating. You can kind of see that the 2 circles intersect in 4 places. It would have to intersect in 4 places. And you can't take 2 disks and intersect them in 4 places.
view them as a circle in the hyperplane.
We're in R2, but all the points are stuck on the hyperplane, so using other things won't help you. Yeah. Okay, so half spaces. There's also Oh, yeah. Okay, sorry. The VC dimension becomes 3 because we can't do 4, and then for intervals, the VC dimension is 2 because we can't do 3. Oh, but we can do 3. I mean, I can draw 3 points and show that we can do all of them. Yeah. The hard part usually is showing that you can't do the x plus 1. I only mention briefly that for hyperplanes, in RD, there's something called Radon's theorem, which is just some classical thing, but it implies that the VC dimension is d plus 1. Okay, I won't do the proof because I want to spend the last few minutes focusing on this one. This is the part that we're interested in. All right, let the range space have VC dimension d, right? Now I'm interested in the growth function. The claim is that the growth function is at most n to the d. Okay, so anything with constant VC dimension has polynomial growth with constant exponent, and so you only need kind of constant size epsilon samples, or 1 over epsilon squared size epsilon samples. Okay. All right. Okay, so let's do this briefly. Okay. So I want to show that g of n is at most the sum of binomials, which is bounded above by n to the d, but we're going to do an induction argument where we want actually the stronger binomial. Okay. So I'll let fdn denote this sum. Okay. And whatever, there's the base cases that are not interesting. All right. In the inductive case, okay, this is where it gets more fun. Let's fix a point set Q with n points, okay, where n is bigger than 0, and fix any point in that set Q. And at some level, I'm going to do an induction where I imagine removing Q. Okay. Now, I can take all the ranges, and I can divide it into 2 sets. They're sort of like ranges that sort of make the distinction of P and the ranges that don't. So let me explain. So, okay, first down here, let's just do, take all the ranges and then subtract P, and you get a range. Okay. But the other set of ranges is sort of interesting. So this is a set of ranges where I'm going to subtract P, but they're only ranges where with P, it's a range, and without P, it's a range. Okay, so this is, if we were doing like disks in a plane and this was my point P, I'm only looking at disks that, and there's some other points or something. Okay, so I'm looking at disks that are sort of like, there's one that contains and doesn't contain P, right? There's sort of matching pairs. Okay, so one disk contains those 2 points plus P, the other disk contains just those 2 points without P. Okay, so all these kind of matching pairs of ranges. Okay, so the claim is that these two families added up, give you the total number of ranges. Okay. All right, so why? Okay, so we have ranges that contain P, but don't have like a matching partner. And then we have ranges that contain P and have a matching partner, which is a range without P in it. And then we have ranges without P. Okay, let me just make sure we go quickly and cheat a little bit. Okay, so if you have a range that doesn't have P and adding P doesn't give you a range, so R does not contain P and R plus P does not have a range, then it's going to be in this bottom set. Okay, so that's class 1. If you have a range that doesn't have P, but if I added P, you also get a range, okay, then that kind of appears in both, okay, and then Okay, and then lastly, if you have a range that contains the point, and if you subtracted the point, it's again a range, then at some level, r minus p will appear up here, and you don't get counted over here. Okay, so what's the point? Okay, um, okay, so even though these ranges here seem to get double counted, uh, it sort of has a matching pair that doesn't get counted. So it works out. Okay, it's not very compelling, but I'm way over time, so I'm just going to have you believe me, such is my power. Okay, but let me explain the point. Is that if I look at the first system, okay, and I imagine removing p, okay. Now those are all the ranges where adding p or not adding p and leaving that is will give you a range in the original set. Okay, so you're going to have VC dimension d minus 1, because if you have a set of d minus 1 points that r sub p can shatter, okay, and if I add p back in, like it can easily shatter p as well, because for every range that doesn't have p, there's also a range that has p. Okay, so I can add back in. So if I have d minus 1 down below, then I get d on when I put p back in. Okay, and the other one has n minus 1 points and VC dimension d. Okay, so I won't do the calculations. I actually was smart enough to prepare this just in case this happened. But the point is that if I'm trying to count these up, then by induction, this is at most, okay, VC dimension d minus 1 over n minus 1 points. VC dimension d, n minus 1 points. We plug that in, we get this sum. Okay? And what I'm doing here, so this sum only goes up to d minus 1. So what I can do is, and this is from I can make this d and then make this I minus 1 down here. Okay? So what is this doing? So what this is ultimately going to be n choose I, but why? All right, so this is the number of ways to form a subset with up to d points. Okay, so out of n points, I'm making a subset with at most d points, and this is like, okay, include p, and then choose d minus 1 points. Okay, and this is sort of like this should be a 1 down here, and this is don't include p and then still choose d points. So this is choosing d points, breaking up into you have to include a point or you can't include that point. Okay, so that's where you get this combinatorial identity, and that is FDN. Okay, so mostly it's about setting up the R sub P, R to the P correctly, so it has this nice recurrence that matches that binomial form, and that's how you get this bound. Okay, all right, then we're done. Thank you.